Push it forward?
Yeah, push it forward fast. Now, I'm going to mark it. Let me see. I have to mark it with, I'm going to use pink, I said. Right, I'll use pink for girls. Although, if you get it in there, it's going to be hard to see. That's all right. All right, you ready? Go ahead. Whoa, that's really good. All right, I got 3 shots. You got 3 shots.
Oh, really?
That's not bad. That's not even on the board. It's like down here somewhere. All right. Ah, there we go. That was a little better. All right, let's see if Jacob can do a little bit better than I can. That's when he works. Here, you have all 3 of them? Where's the 3rd one? Somebody see the. All right, okay. All right, now we're going to use blue for boys. And hopefully there'll be 3 on the board this time. You ready? Okay. All right, hold on. Slow down. I'm not still in the way. You catch those when they come off. All right. Getting better. I think the boys are ruling. Yeah. Sorry. All right, now my turn. And I'll be black. Okay? I'll use black. Do I have all 3 in there?
2.
When did I go? Or is it 3rd? Oh, there it is. Thank you. All right, my turn. You ready? I don't need to go back there. All right, it's all right here. By the way, I'm always amazed that none of these leave a mark on the board. I mean, they hit pretty hard, but it's hard to get them to leave a mark. Anyway, all right. Now, let's look at those, and we're going to talk about something today. Something accuracy versus precision. Now, see if you guys can figure out the difference. First of all, who do you think was the best shot as far as boys versus girls? Who won? Boys won. All right, that's easy enough. They don't always win, by the way. But boys won this time. All right, how would you know that? Because you'd say their shots are what? There's 2 words now we could use. Accuracy or precision. If I use the word accuracy, what do you think was the most accurate shot we probably have here? What do you think accuracy means? What would you call it? Would you call this shot accurate or would you call it precise? Would you call this shot accurate? Well, probably not. Or precise. How about these guys over here? Well, it turns out there's a difference between them. Okay? Accuracy is how close you are to the bullseye. But the most precise shots were the ones I shot over here. Because I did the same thing in the same spot all over the place. What do you call them? Shooters on the team, right? Right, you're on the rifle team. That's the word. Rifle team. Like a mental block. You guys, who would you rather have shooting for you? All right, would you rather? If this guy would win this particular target, all right. But basically, wouldn't you rather have this? Because what could you do to a guy like that? You just move the sights like maybe 3 clicks left and 1 click up, and he'd be right in the bullseye. He's shooting the same way every time. He's got precision. He happened to get an accurate shot here. Oh, she had an accurate shot, but her other one was up here and her other one was down there. You don't really want that. You want somebody to shoot the same way over again. Sorry, Lexus. But that's nothing I can do about it. It's well, you could actually get better at it. But anyway. All right. So here's my question to you: what do we want in chemistry? Accuracy or precision? Precision? No.
Accuracy.
No. Both. Yeah. Yeah, you want both. All right. You want to get the right answer, but you also want to be able to do it multiple times. Many times when we do an experiment, you don't, not many times, every time you do an experiment, if you're going to do a study, if you're going to study something, does this cure cancer? Does this food cause cancer? Whatever. If you're going to study something, you don't just do it once. You do studies over and over and over and over again, and you do it with large numbers of people. Why? Because you want to make sure you've got repeatability of your experiment. That's what precision is, how repeatable it is. But you also want to get the correct answer. You want to do it very accurately as well. We'll be shooting for both, and we'll be measuring both in our labs. We've done quite a few labs already in just the first chapter. You're going to do 3 more labs in this chapter. Every one of the labs we do in this chapter, pretty much, with the exception of the first significant figure lab, is going to require you to calculate the accuracy and the precision of your experiment. And the accuracy is going to be measured by something called percent error, and the precision by deviation. We'll talk about that both when we do these. Okay. All right. So get your notes out. This is picking right up where we left off yesterday with things we measure. Well, we talked about the things we measured yesterday. Now we're going to talk about how we can determine how well we measure them. All right. Accuracy versus precision. And they're not the same, even though we use them interchangeably. If you think about it, all of yesterday too was like heat versus temperature, mass versus weight, unit versus quantity. All of those were things we often get confused. This is another one. This will be on the test, and it won't just be on the test. It will be used all year long. Calculate your accuracy and your precision of a lab. By the time this year is over, you'll have calculated percent errors for accuracy probably half dozen or more, maybe a dozen times out of the 30 labs we're going to do. All right, let's start with accuracy. What is it? As I just showed you with my little demonstration here, it's the nearness of a measurement to an accepted value, how close you are to the bullseye. Nearness of a measurement to an accepted value, how close to the bullseye. The shot that was hit right by the bullseye, that was the most accurate shot. But if I only have one shot, I can't talk about its precision. We'll talk about that when we get to it. But let's stick with accuracy for right now. Okay? All right, there are two ways we're going to measure accuracy. All right, actually, the first one is just kind of your preliminary step to getting the second one. We're going to call it the absolute error, just how far physically the thing is, your value is from the correct value. And then we'll do the percent error, which is much more useful. Okay? So the absolute error, or the EA, the accepted is just simply the accepted value minus the observed value. Okay, that's the formula for it. Accepted minus observed. What you should have gotten minus what you did get. Okay? And remember, yesterday we were talking mostly about numbers, things we can measure with numbers. So that's what we're going to be doing. We're going to be measuring things, calculating things, trying to find correct answers. All right, there is a correct answer. We measure our thing, we get this answer. The difference between them is just the EA. Very simple to do. Let me show you in a quick example. Say I was doing a lab. All right. By the way, I forgot to tell you, another words for these are the theoretical versus the experimental. There's two other ways I could say the same thing. The theoretical value is your accepted value. It's what you were shooting for. It's what you wanted to get. The experimental value is what you got in your experiment. It's the observed value that you saw. All right. Now, let me show you a little. Say we're doing a lab. One of the first labs we're going to do is we're going to try to measure density. All right. We're going to measure density of an object. We're going to measure density of zinc. Okay. Let's say I want to make a chart right here. Make this little chart. Let's say I do two experiments where I'm doing two different metals. And I'm going to give you some data. We're going to plug it in there and see if you can tell me what the EA is. This is very simple. So make this chart, and we'll fill it in. Very, very simple stuff here. All right, you make a chart?
Yeah.
Oh, yeah. Okay, for experiment A, let's say the correct answer, the accepted value, was 10 grams per milliliter. Wait, did I actually write this in here? I know, I'm still on black. That's right. 10 grams per milliliter. That's what I should get. Let's say I should get 10 grams per milliliter. Now, I do the lab, and I get 9.8. Who could tell me my error? Very simple. What would the error be, Gabe? 0.2 grams per milliliter. By the way, we're going to talk about something called significant figures in the second half of this class, and I'll tell you why that's not correct as far as significant figures go, but don't worry about that for now. Right now, we don't know about that. All right, so that's easy enough. Now, let's say I do another experiment. I'm using a different metal, and the density of that metal is supposed to be 40. grams per milliliter. And I get 40.2 grams per milliliter. What's my absolute error? What's my absolute error? What do you think? I was hoping to get that. She said negative 0.2. No. And I purposely didn't point this out to you earlier. Did you notice these two lines here? Do you know what they mean when they're around the value? Absolute value. Exactly. Absolute value, okay, which is what this, that's why it's called absolute error, means that when I subtract two numbers, I only care about their physical difference between the two. I don't care about their sign. I don't care about if it's a positive or negative. The answer is still 0.2 grams per milliliter. Even though you subtracted, you got a negative. An absolute value just means the difference between two numbers without regard to their sign. I don't like, unfortunately, many of you guys learned, and it's not incorrect technically, but many of you learned that it's the distance from zero. How many of you learned that, right? Absolute value is the distance from zero. I don't like that because, for example, if I have two numbers on a number line, and I've got minus 5 here and a positive 10 here, and I want to know the absolute value of the difference between those two numbers. Again, there's two different numbers, neither one of which is 0. So really, the absolute value of the difference between those is what? If I subtracted those two numbers, what would it be? What's the difference between these two guys on a number line? Simple. 15. Okay? So I guess technically you can add up how far from 0 here, how far from 0, add those two guys up. I just don't like thinking of it that way. I just like thinking of it as the difference between two numbers, just the physical or absolute difference between two numbers without regard to sign. All right? Because it's not always a difference from 0 necessarily. But, you know, different people teach it differently. Good enough. So these guys, according to this experiment, according to the way I did my accuracy, would appear to have exactly the same error. They're the same accuracy. But they don't. And as we'll see in a minute, because this is only absolute error and it's not very useful. All right? Absolute error is just a tool to get me to something else. And that is percent error. Percent or relative error is more useful, and I'll do this more often in chem. And in our labs. We're going to be, I mean, granted, you have to do the absolute error to get the percent error, but still. The relative error, or the percent error, is the percentage by which an observed value differs from the accepted value. This is a much more useful thing. And you, by the way, I'm almost sure you'll be calculating percent errors in physics class as well. Have you done any yet? Have you done any labs yet? Okay, I think you will be. All right? Pretty sure. Because physics cares about how accurate you are as well. Okay? All right. So how am I going to get this? Here's your formula for percent error. Now, before I give it to you, let me ask you something about percentages. Okay? You guys know how to get a percentage, I would think. For example, if I wanted to get the percentage of girls in this class, what would I do? Raise your hand. Who knows how to get the percentage of girls? See if you can get it right. Percentage of girls in the class. Lex.
The girls are divided by the boys number.
No. Good, bad answer. I'm glad I'm getting these wrong answers. It's not the number of girls divided by the number of boys. Anybody else have an idea? What do you think? Number of girls divided by the total number in the class will give me the percentage. Okay? Say I wanted to get the percentage you got on the quiz. It's very easy. If you got 9 out of 10 on a quiz, what did you get, Jennifer?
A 90.
A 90. Okay? If you got 10 out of 20 on a quiz, what did you get, Sydney? A 50. What are you doing when you did that? When you got 9 out of 10, 10 out of 20, and you got your percentage. Here's what you did in all 3 cases, by the way, including the girls over the class. You took the part, don't write this down, this one, the part over the whole times 100, didn't you? Right? Because the part over the whole, like the 9 over the 10, gives you a decimal, which would be what, in this case? 0.9, right? right? And then when you times that by 100, that tells you out of 100, you get 90%. See? And that's what you do. So basically, if you know that, you know how to get the percentage of anything. It's always going to be the part over the whole times 100. So, for example, I always amazed when people say, "Oh, I got 35 out of 40 on the quiz. What did I get?" What do you have to do to get your percentage from 35 out of 40? Divide 35 correct out of 40 total questions and times by 100. Now, it's not going to be a nice, easy number you can see in your head, but that's all you do. You get a calculator out, you do it. All right? That's exactly what we're going to do here. Watch. The formula for percent error is going to be the part you got wrong. What do we call the part you got wrong from number 1? How much was wrong? The absolute error, right? So it's going to be the absolute error over the accepted. That's what you should have gotten, the correct total amount, times 100. So the part over the whole times 100. The part that was an error over the total amount times 100. By the way, if you're wondering why you're going to get used to this. A lot of people, I see their faces out there when I'm talking about formulas like this. It's like, just give me the formula. Shut up already. Give me the formula. I don't want to know why it looks like that. I want to memorize it. All right? And that's what you all want to do. You want to memorize your way through stuff. But unfortunately, the problem with memorizing things is that you really can't memorize your way through life. You can't memorize everything. It's much better to understand it. I can apply the knowledge of part over the whole time, understanding that, to the percentage like you're going to have to do throughout the year. We're going to do percent composition of compounds. It's going to be the same logic, part over the whole times 100. We're going to do percent error. We're going to do percentages of other things as well along the way, and it will always be part, if you understand it, over the whole times 100. You won't have to memorize, oh, this guy is EA over 7, EA over 7. And that's what some people will do to study. They think they're studying when they're going, EA over 7, EA over 7. And they're memorizing that formula. But you don't have to memorize that formula if you understand it. Same as I showed you with those charts the other day with endo and exothermic. All right, so there's your equation. Well, either way, I know most of you won't listen to that. You probably will memorize it, and you'll do okay on the test. But that's how you get the percent error. Let's do the same thing for those two experiments again. Just give about 2 lines in between experiment A and experiment B. Just give a couple of lines here. Let's do the same thing. To get the percent error for experiment A from a minute ago, we just did, I will take, here's my formula right here, percent error equals, what was the EA? What was the EA from experiment A minute ago? 0.2. 0.2 grams per milliliter over what? What was the accepted for experiment A? 10 grams per milliliter, and then times by 100. Now, before you grab your calculators, I love this. We're doing, Katie back there has got her calculator out, and she has her calculator out because she's subtracting 2 numbers for electronegativities, which drives me crazy. Do you need a calculator to do this calculation? What can I do to make this problem a little bit easier? Let's just take a look. 0.2 over 10 times 100. If I gave you this, could you do this problem? 2, oh, don't write this down. 2 over 4 times 8. What would you do in that case? Wouldn't you go like this? 4 goes into 8 2 times. 2 times 2 is 4. Is that a nice, easy way to do it? And can't I do that here? Right? Times 0.2 is what? What's 0.2 times 10 is what? What am I going to do to the decimal if I'm multiplying by 10? Move it 1 space, right? So that will be 2% error. You don't need a calculator to do something as easy as that. But again, that's the difference between thinking about a problem, understanding a problem, and then, no, I got to just plug and chug and memorizing. That's what you mostly have learned to do your whole life. Okay? You've been taught to do that, and that's partly our fault. But you've got to get out of that habit. You've got to be able to understand things. Let's try this next one. Experiment B, and we'll see what happens. According to a minute ago, I should have the same error. A minute ago, I calculated the error for experiment A and B, and it was 0.2 and 0.2. They were exactly the same. But let's see what happens here when I do the percent error for this guy. The percent error for experiment B is going to be, what's the EA for experiment B? Look back at your notes. What is it? 0.2 grams per milliliter again. over, what was the accepted for that guy? 40. Times by 100. Well, you can grab a calculator for this one if you can't see it. But again, it's not that hard. All right? I can do this one. Last one I did by dividing these two out. Can you see an easier way to do this one?
Did you just say it's not that hard?
I did.
Did you just say that? Class is hard.
This is
Isn't
easy.
it?
Wait.
Class is easy. What's that?
That's chemistry, man. Where'd my other ball go?
Ball. That's not chemistry.
Where'd the other ball
That
go?
looks extremely.
Oh, there we go. Thanks.
Caleb, is this class hard?
No way.
That means right. Not that easy.
Get out. Get out.
That didn't hurt. Hit me again. This wasn't bothering me.
I got one time, just out of
I
the
didn't
blue.
ask. No.
Yeah. Just want to get rid of him. Tell him a story. Now, Mr. Gunther came in one time. Short, that's all. And just opened the door and I blasted him. He almost peed his pants. All right, now this one I looked at and I went, I did this into that, gave me 10, 10. Can you see an easy way to do this guy? Instead of dividing him into 40 into 100, I don't know. But if you times 0.2 by 100, what do you get? Move the decimal place, how many spaces? 2. So you have 0.2 times 100 would be what? 1, 2, you have 20, right? What's 20 divided by 40? It's half, right? Which would be what in the decimal? 0.5. I mean, granted, I don't expect, by the way, as much as I don't expect that Katie needs to use a calculator to subtract two numbers, making fun of Katie today, and I don't expect you would have to do this in a calculator either, you can. Everyone has it. Will have a calculator. I'm going to show you what kind to get probably by the end of this week. All right? Everyone has a calculator. You can use a calculator. I don't care if you use a calculator. But the fact is you should be able to understand it. Now, final thing to say about this guy. Who's better? Who was actually the better experiment? Who actually was more accurate at the end of the day? Experiment A or experiment B? I'm always asked this because I'm always amazed that some people have to think about this. Who was better? B. He has less error than A, right? He has less error than A. He was more accurate. Why was he more accurate? That's the question. Why was experiment B more accurate than experiment A? And the answer, you can look at it from math perspective, because that's a 40 and that's a 10. But in common sense perspective, here's why. Common sense. Let's say I gave you this ruler, and I said, measure the length of this index card. And you did it. And you were off by 2 inches. Did you do a very good job? No. Now, I gave you the same ruler, and I said, measure the length of the entire building, and you were off by 2 inches. Did you do a good job? Yeah, you did pretty well. You got pretty close to the right answer. You see why? The size of the sample matters, okay? The size of what you're measuring matters. All right? You can't take small errors become bigger if you only have a very small thing you're measuring, okay? So that's the reason why. Very small. That's why you want to have a larger sample. Okay, a larger thing that you're measuring, the bigger one, the easier it is the more room for error without causing real problems. All right, good enough. Y'all understand how accuracy measures how close you are to the accepted value, how close you are to the bullseye, and we're going to measure it using percent error. Now, the other one I said I want to talk about was precision. Precision is different. I cannot have a single shot on that bullseye and say it was precise. Because precision measures the agreement between 2 or more values. You probably need that, huh? That's the backside? Yeah. Hold on, I think I have them written down here. If I don't, I'll have to give it to you later because I might have them here. I had a paper. What is that? 17th and 18th. There's one more to come. All right, I'll have to find it. Just give that one to you, okay? You can do those two for right now. All right, so you have to have more than one shot. I can't say I have a precise shot. I can say I have precise shots, multiple ones, okay? Because it's the repeatability of an experiment, not how close you are to the accepted value. It makes no difference. Remember when I shot my 3 shots over here to the side? I purposely didn't shoot them in the bullseye. My shots were way more precise than the girls' or the boys' shots. But they weren't any more accurate than theirs. Matter of fact, in most cases, they were pretty much less accurate, with the exception of Lex. All right. We're going to use average deviation. I mean, there's a lot of ways you can measure precision. This is the easiest way. If you take a stat, anybody in stats and probs in here? Okay. If you take stats, you'll learn about standard deviation. Have you done that yet? No? Variance, standard deviation, and other ways we can measure precision. Okay? They are a lot more complicated. When you go to college, you'll learn how to do them and apply them to experiments. We're just going to do a very simple form of deviation called average deviation. It's going to measure how much our values differ from the mean. Okay? From the mean. What do you think the mean is besides me when I shoot Mr. Phillips? Yeah, the mean is just another name for the average. So it's the difference from the average, okay, of each of the values. And what are the average difference of each of those from the values? So the equation looks like this. And again, it's an absolute value. Absolute value meaning whatever you get as your answer, it's still positive. Okay? The value of a number without regard to its sign. Just the absolute difference between two numbers. So if I subtract two numbers and you get a negative, it's still positive. All right, now I'm going to make a chart here and do another experiment. This is another thing. Not only do I want to make sure I'm measuring something large enough to be measured, okay? I wouldn't want to use this ruler and try to measure the thickness of this paper, okay? It'd be very difficult to do it accurately, all right, for accuracy's sake. But I also want to make sure I do it over and over and over again so that I can measure its precision, okay? I want to make sure I measure something multiple times and then take the average of it. Because, you know, every now and then I might make a mistake, and this will average out the mistakes. All right? They won't show up as much. They won't affect it as much. So here's what you normally do in a lab. Like if you're doing an experiment, in real experiment, like if you're doing research on something, you don't just inject one mouse with this virus and see if it kills him or if it cures this disease. You inject hundreds of mice. Thousands of mice, and you see what happens to them over time, and then you take the average of the data. Okay, if you want to see if this is going to hurt something or cure something, you don't just do it one time. So, if I wanted to measure the density, for example, again, we'll stick with something simple like density. I'm going to do it multiple times. Let's say I'm going to do it 5 times. Make this chart also in your notes there, and I'm going to do the same exact thing. Last time I said I measured one mass or one density of one metal to be 10 was supposed to be, the other one was supposed to be 40. Well, now I'm going to say this is more like what you're going to do in lab on probably by Thursday or Friday of this week. You're going to do the same thing over and over and over again, measuring the same one. Now, I realize that would be very boring, by the way. So I'm not really going to make you measure it 5 different times and calculate the density 5 different times. I'm actually going to do this when we do this in lab. I'm going to divide you into 2 parts. That side of the room over there, everybody on that side of the room, there's like 6 groups over there, and everybody on this side of the room, there's 6 groups over there. We'll average the data from this side, compare it to the data from the other side, if we're doing something. But technically, you should be doing it multiple times yourself. All right, let's fill these in and see what we can get here for this. Okay? Let me give you some data. Let's say I did this experiment. You are going to be measuring the density in 2 different labs this chapter. Well, let's say I measured the density of my object I was trying to measure up. And I measured it to be 10. Oops, no, I fit them already in there. Good. 10 for the first one, 12, 8, 9, 11. I do it 5 times, and that's the answers I get. Notice they all kind of are a little bit off, but they're close to each other. That's not unusual. If you do the same thing multiple times, you're not going to get exactly the same answer every time. You know, for whatever reason. A little bit of error. There's still one more to do. I got to give it to you in a minute. Okay, just give me a second. All right. Can you all calculate the mean for that? What do you think it's going to be? It's very simple. I purposely did it this way. Again, use a little common sense. Yeah, it's going to be 10. Notice this guy's 2 above, that guy's 2 below 10. This guy's 1 below, that guy's 1 above 10. So if you did this all in your head, you would get a mean of 10. Oops, I'm going to use green here. 10 grams per milliliter. Now, how would I get the deviation of each of these? For each one of these trials, I would have to take the observed minus the mean. Well, here's your observed value. These are your observed values, and that's the mean, right? So I would take, in the first case, 10 grams per milliliter minus 10 grams per milliliter, and I would get 0 grams per milliliter. What would you do for the second one? 12 minus 10. What would I get there? 2. Let's see if Gabby learned. What are you going to do for this next one, Gabby? 8 minus 10 gives you what? Exactly, not negative, because we're taking the absolute value of these things. So it's still going to be 2. There's a good reason you don't want to put your negatives in here, people. Can anybody figure out what's going to happen if you kept the negatives for this? Can you figure out? Well, keep thinking about that while we do the rest of these. 9 grams per milliliter minus 10 equals 1, and 11 minus 10 equals 1. What do I have to do at the end here? What do you think I'm going to want to do? I want the average deviation, right? How would I get the average deviation? What am I going to do to all these values here? How would I get the average of them? What do you think? Well, how do you get the average of anything? Add them up and divide by how many I have. 1, 2, 3, 4, 5. I add these guys up and divide it by 5. I got 10. Add all these guys up, divide by 5. And in this case, I'm not saying there's an easy way to do that when you probably don't have it in your head, but it's going to be 1.2 grams per milliliter. Can anybody see what would happen if you kept the negatives in these? What would happen to your average deviation every time? What would it be? Think about it. This guy would be negative. This guy would be negative. What would you always get when you added them up? 0. Yeah. All right. So that's why, another reason why you don't keep. You keep the absolute value. You're talking about the difference between them, the absolute difference between them. All right. So there you have it. Now here's what you're saying at this point, people. And again, technically this isn't correct. But it is correct. But it's technically a better way to do this would be to use standard deviation, not just average deviation. However, it's useful enough. All right, you're saying that, and this is the average, by the way, average deviation. You're saying, when you did this experiment, I think the answer is 10. But according to my data, I wouldn't be surprised if it's as high as 11.2, or if it's as low as 8.8. You see? It can be higher or lower by 1.2 from that average. And so your final way of reporting your data would be this. Watch this. I think I can do this. Your final way, don't worry about that. Final way of reporting your data would be the mean plus or minus the average deviation. The mean plus or minus the average deviation. Let's write that down underneath this. So you would say, I think the answer is 10 grams per milliliter. Plus or minus 1.2 grams per milliliter. Okay? All right. Now, your homework is already on the board over there. It's page 52, numbers 75 to 78. All right? It's on the board over there. You can, by the way, yesterday I did not tell you, so we kind of ran out of time. But that's the homework from yesterday, 1 to 6 on page 21. All right? Page 21, numbers 1 to 6. Start working on that now, because we are going to do something completely different next period, but I need to, Katie's got one more essay to ask. So I'm going to stop this here, and you can work on that.